Hello everyone, I am Dr. Rajesh and I welcome you in this video lecture. And in this video lecture, we will prove an important result of divided difference, and the result is prove that Newton's divided difference are symmetric function of their arguments. Symmetric function means the order of the arguments doesn't matter and the result will be same irrespective of their order. For an example, we will be proving it by principle of mathematical induction. Fine. Let us prove the result for n is equal to 1. First order Newton divided difference. We know that first order Newton divided difference is f of x naught x1. You know this is equal to, you can either take x1 minus x0 or x0 minus x1, whichever you want you can take it. Fine, so this will be x1 minus x0. So can I write it something like f of x1 divide x1 minus x0 minus f of x0 divided by x1 minus x0. Can it further be written as f of x1 minus x0 plus f of x0, that is x0 minus x1. Now we have written it like that, so this can be written as f of x0 divided by x0 minus x1 plus f of x1 divided by x1 minus x0. So it can be written as summation starting from f of x0 divided by x0 minus x1. Fine. So, and here you could write that which elements are in the symmetric order. x0 and x1 are in a cyclic order. Like after x0 you will get x1 and after x1 you will get x0. So you will write below the summation x0 comma x1. So this could be written as this summation starting from x0. When you will write f of x1 x0, so this could be written as f of, based upon the same result, f of x1 divided by x1 minus x0. Fine. So we'll see, and you will write that x0 and x1 are in cyclic order. So we'll see that whether this result is same or not. Okay, we will try to expand it. We'll write f of x1 divided by x1 minus x0. What you get after x1? After x1 you get x0. Fine. So this will be, after x1 you get x0 and after x0 you will get x1. So this is in cyclic order. So after x0 you will write x0 and after x1 you will get x0 and after x0 you will write x1. So this is the result which we will get for x1 comma x0. Is it same as this one? Yeah, please tell me. This is same. So we can say that this is nothing but equal to f of x1 comma x2, implies f of x0 comma x1 is symmetric function. Therefore result holds good for first order divided difference, that is n is equal to 1. Now we'll prove that result also holds good for n is equal to 2. Let us take third order divided difference, that is x naught, x1 and x2. So we'll take the last two, f of x1, x2, then we'll take first two minus x naught, x1 divided by x2 minus x naught. Fine. This is further equal to, now from the above result, what we can write instead of this x1 and x2, it can be written as sum of, so I am writing these x1 and x2 are in cyclic order, so it can be written as f of x1 divided by x1 minus x2 plus f of x2 divided by first x2 then x1. Fine. Minus, because result is holding good for n is equal to 1, so we can write it from any of the argument. So we can write it as f of x naught divided by x naught minus x1 plus f of x1 divided by x1 minus x naught. Fine. So outside is 1 by, it is x2 minus x naught. So now collect the same terms, like we are going to collect f of x1, and I am going to write it as f of x2 divided by x2 minus x1 plus f of x1 is common, and here is 1 by x1 minus x2 minus 1 by x1 minus x naught minus f of x naught divided by x naught by x1, and outside is 1 by x2 minus x naught. This thing is further equal to f of x2 minus x1 plus, now take the LCM, it will be x1 minus x naught, it will be minus x1 plus x2 divided by x1 minus x2 x1 minus x naught, and minus is negated, I am going to take inside, this will be f of x naught divided by x1 minus x naught. Fine. And outside is 1 by x2 minus x naught. This will cancel out, so we are left with x2 minus x naught, and outside is x2 minus x naught. So this will be, so I am going to write it as f of x2 minus x naught, because this will come inside x2 minus x1 plus f of x1, x2 minus x naught will cancel out, so we are left with x1 minus x naught, x1 minus x2 plus f of x naught. This is, and you know this is x1 minus x naught, so I am going to take common so that I could write x naught first, x naught minus x1, and from here I am also going to take minus common, minus minus will be plus, so this can be written x2 minus x naught minus x2. So this can be written as, first I am writing this one, f of x naught. Now we will try to understand the result, plus f of x1, that is x1 minus x naught, x1 minus x2, plus f of x2 divided by x2 minus x naught, x2 minus x1. This implies that f of x naught, x1, x2 is equal to f of x naught plus x naught minus x1, x naught minus x2. Now starting from this I will write the rest of the two terms, and in fact starting from any of these terms we can write the rest of the two terms. Now see, x naught, x1 and x2, these are in cyclic orders. So now let me write with the help of this one, let me write next term. After x naught you will get x1, and after x naught you will get x1 minus, as such after x1 you will get x2, fine, and after x naught you will get x1 minus, after x2 you will get x naught. Is it same? Yeah, x1 minus x naught here, x1 minus x2, same, plus similarly with the help of this one now we'll write the next term. After x1 you will get x2, and after x1 you will get x2, after x2 you will get x naught, after x1 you will get x2, after x naught you will get x1, fine. So I could also write it something like summation starting from any of the term. So I am taking first, because here it is starting from x naught, so I am taking f of x naught minus x1, x naught minus x2, and here you will write that x naught, x1, x2 are in cyclic order. You can write it as are in cyclic order, fine. So this is if we write why now we have reached that it is symmetric, I will show you. Instead of this one, if I write it as f of x1, x2, x0, in this order if I write it as, fine. So what will you, from the first I will write f of x1, x1 minus x2, x1 minus x0. Now with the help of this I will write the next term by using this one. Next term will be plus f of, after f of x1 you will get f of x2, after x1 x2, after x2 x0, after x1 x2, after x0 x1, fine. With the help of this one, next term f of x0, x2, x0, x1, x0 and x2 are the same terms. Yeah, this is the term here at third place and here at first place. This is in the middle and this is at the first place. This is at third and this is in the middle. So all the terms are same. Though we have written x1 first, result is still same. So order is not mattering here. You notice that order is not mattering. If I write it something like x2, x1, x0, result would still be same. So from here I could easily infer that I could easily infer that this implies that f of x naught comma x1 x2 are symmetric function of their arguments fine, means we can, whatever way we write it, the result will be same. If we write it something like that, it is same. If we start with x1, we write it as x naught x2, result will be same. If we write it as x1 x2 x naught, result will be same, and any number of permutation we make, the result will be same. So this is the second order divided difference, so implies result hold goods for n is equal to 2. Now we have shown that result is holding good for n is equal to 1, n is equal to 2. Now we will suppose that result is holding for any number n is equal to k, and we will show that result also holds good for number k plus 1. So we'll assume that result is holding for kth order divided difference, and we'll prove that it also holds for k plus 1th order divided difference. Then this will complete the induction and we'll get the required result. Okay, fine. So let us assume that result holds good for n is equal to k, that is f of x naught x1 x2 up to xk minus 1 and k. So this contains k plus 1 term, so it is of order 1 less, means k. So this can be written as sum of, starting from x naught, I am writing f of x naught divided by x naught minus, leaving x naught minus x naught term only, because that will make it infinity. We are writing other terms, x naught minus x1, x naught minus x2, and the last term x naught minus xk. Fine. Now next term f of x1 you will get, starting from here, you can also write, or x1 minus x naught, it will be x1 minus x1 minus x naught, x1 minus x1 will not be taken, so x1 minus x2 up to x1 minus xk. Fine. And it is further plus, and so on. You can write the kth term, it will be f of xk divided by f of xk minus first xk minus x1 second, and so on. You can write xk minus xk is to be left, so xk minus xk minus 1. Okay, and name this equation as equation R-stick. Fine. Now we have to prove the result for, we shall show that result also holds good for n is equal to k plus 1. So let us do it. We know that k plus 1th order will be x0, x1, x2 and so on up to xk plus 1. Now starting from x0 to k plus 1, these are k plus 2 quantities. So it is divided difference of 1 less means k plus 1. So by definition it can be written as, we will take last k plus 1 values. So it will be f of x1, x2 up to x k plus 1 minus, now take first k plus 1 quantities, f of x0, x1 up to, you can write as one preceding, also write xk minus 1 xk and divided by xk plus 1 extremities point, xk plus 1 minus x0. Now using the aristic equation says that the kth order divided difference can be written as sum of these quantities. So this is kth order, this is also kth order. So this result can be written for both of these two. So using the result for kth order, because it is holding good, so I am going to put the values over here. So what it will be based upon the above equation. So this will be, write it as, outside you know it is k plus 1 minus x0. It will be f of x1 divided by, starting from x1 minus x1 will not be taken, so next argument x1 minus x2, next argument x1 minus x3 and last is x1 minus k plus 1. Fine. Now next will be f of x2. It will be x2 minus x1. It will be x2 minus x2 will not be taken, x2 minus, though it is not written but it is there, x2 minus x3 and it will be x2 minus x k plus 1, x k plus 1. Similarly it will go like that, and here we will write the last term. If you want to write kth term, you can also write f of xk. It will be xk minus x1, first one, xk minus x2 and xk minus k is not to be written, otherwise xk minus k minus 1 and after that k minus k is left. So last I am going to xk minus k plus 1. Fine. Now writing the last term, f of x k plus 1 divided by x k plus 1 minus x1 x k plus 1 minus x2 up to x k plus 1 k plus minus k plus 1 is to be left, so we will write this one. Okay, fine. You can enclose it in the curly braces. So this is done. Now next we will write this thing. For this one we will write the result, because it is also kth order and result is holding good for kth order, so we can write it as a sum as given in aristic. So I am writing it for this one also. Okay, So this will be minus curly braces over here. So I have to write the result for this one. Fine. So write it. This will be f of x naught. This will be x naught minus x naught will not be taken, x naught minus x2. After x1 it will be x2 obviously. So 3 dots x naught minus xk. Fine. Plus f of x1, it will be x1 minus x naught. x1 minus x1 is not to be taken, x1 minus x2, and so on. It will be x naught minus, last is x naught minus. Fine. Now k minus 1th term, if you want to write, you can write. Otherwise it is wholly up to you. If you want to write kth term, you directly write the kth term here, because I will make the combination with this kth term here. So f of x k will be xk minus x naught, xk minus x1, and so on. It will be xk minus xk minus 1. This is curly braces. Fine. And this is the square braces that we have closed. Fine. So now we will collect. First we will write f of x naught term. Where is f of, this is f of x naught. So for this k plus 1th order, it will be x naught minus x1. Here is this x naught minus x2, x naught minus xk, and x naught minus xk plus 1. So here the sign is opposite. So I am going to write this is further equal to f of x naught, this one x naught minus x1, x naught minus x2, x naught minus xk. Here is minus sign, and this will come inside and multiply over here. So I am going to change the sign, adjust minus over here. Instead of xk plus 1 minus x naught, I am going to write it as x naught minus xk plus 1. So this thing is done. First is done. Now next we will do it for fx1. I am going to collect this term and this term. Okay. Now collect these two terms. F of x1 is common. Fine. So this will also be divided by x k plus 1 minus x naught. Now what we will get? x1 minus x2, x from here, this and this, x1 minus x naught, no, x1 minus x2 is here, x1 minus x3 will also be here. So x naught minus xk. So here it is x1 minus x, its preceding term will be something like x1 minus xk. Fine. So this will be common. This thing, except this thing will be common. So I am going to take common from these two. It will be x1 minus x2, x1 minus x3. It will be after this term, x1 minus x3 up to x1 minus xk. And inside we are left with x1 1 by x1 minus xk plus 1 minus 1 by, it will be x1 minus x naught. Fine. Now we will write the last term and so on. It will continue, and in the end we will get f of xk plus 1 this will be divided by x k plus 1 minus x naught. Fine. So this will be x k, leaving other terms because we first two and the last term we have obtained. I am leaving the in between. These are obvious term and that will be done similarly, that we are doing like a 4fx1, and these terms were only the single terms present, so there is no pairing with these terms, so these were the single terms. So I'm going to write this one, x1 x k plus 1 minus x2 up to x k plus 1 minus xk. Fine. Now this is further equal to f of x naught minus x1 x naught minus x2. Now only writing the last term, x naught minus xk plus 1. So this will be this thing plus, now writing this one, f of x1. Now you take the LCM over here. Let me write it at least for once. x1 minus x2, x1 minus x3, and x1 minus xk. It will be, take LCM, x1 minus x naught minus x1 plus x k plus 1 divided by x1 minus x k plus 1 x1 minus x naught. This x1 to x1, x k plus 1 minus x naught. So this will also cancel out. So plus this term as such, x k plus 1 divided by k plus 1 minus x naught k plus 1 minus x1, and you can, if you want, you can generalize it. You can leave it, your first two terms has been written. Now write the last term. It is up to you, as per your convenience you can write the terms. If you require, you can write its preceding term also, its succeeding term also. You can make them appear anytime, and you may omit them anytime. So it is as per your convenience. So this is the result, and next we will be writing this as f of x naught divided by x naught minus x1, x naught minus x2 up to x naught minus xk plus 1 plus f of x1. Fine. Now x1 minus x naught, this term. Fine. x1 minus x2, x1 minus x3 up to x1 minus xk plus 1. Fine. So plus last term is f of x k plus 1 divided by x k plus 1 minus x naught x k plus 1 minus x1 up to x k plus 1 minus xk. Fine. Now I am going to write it as summation. Fine. F of starting with x naught minus x1, x naught minus x2, and so on up to x naught minus xk plus 1, and rest of the term of this summation will be written with the help of the result x naught, x1, x2 up to xk plus 1 are in cyclic order. Fine. So you can easily write the other terms with the help of this cyclic order result. And these three dots, why I am using again and again, these three dots are standard and these are pronounced as dot dot dot. Fine. And it is known as ellipses. Okay, so this is standard. Instead of dash 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 we write three dots. That means in scientific writing you write the three dots and that is known as ellipses. Fine. So this shows that this we have written it as this sum where x0, x1, xk plus 1 are in cyclic order. This implies that nth order k plus 1th order divided difference is symmetric function of their arguments. This further implies that result holds good for n is equal to k plus 1. This completes the PMI. This completes the principle of mathematical induction. Implies result holds good for every natural number. Fine. So result holds good for every natural number. So you can write it like that. So this will be implies result holds good for n is equal to k plus 1. Therefore, by principle of mathematical induction, this completes the induction. PMI, we can say that Newton divided difference of any order is symmetric function of their arguments. Newton divided difference of any order is symmetric function of their arguments. That is, result holds good for all natural number where n belongs to set of natural numbers. So this completes the proof. So in this lecture we have studied the proof, and in this we have proved that it is symmetric. Newton divided difference are symmetric function of their arguments. Fine. So that we have proved it, and proof is shown over here that we have done. And this question is important from examination point of view, and you should go through this question, and this is important. So in this lecture we have proved that Newton divided difference are symmetric function of their argument. So what is the meaning of this theorem? If we are asked to find divided difference of x0, x1 and x with respect to these arguments, and in other one we are written first x, then we are written x0, x1. then the result will be same, because we have just proved that Newton divided difference are symmetric function of their arguments. The order of the argument does not matter, result will be same. So this will be the second order divided difference, so result in both the cases will be same, though here x is present at third place, here at first place, so this does not make any difference, and even if x is present in between, still the result will be same. Fine, this is comma, this is comma, so result will still be the same. So that is the beauty of this result, that whenever we want to switch the order of the arguments, we can switch to our convenience, and that we will be using in the Newton divided difference formula proof also, so that we will be making use very frequently. So that is all I have from this lecture, and if you have liked the lecture, please like, subscribe, share and comment. Your comments in the YouTube section, in the comment section, are valuable and welcome. This is Dr. Rajesh saying goodbye, take care, bye bye, and see you soon. Thank you very much.